Okay, why don't we get started? Administratively, there's a homework due this evening, the usual 1 second before midnight. Please make sure that you uh, do the accounting of the various components involved in the question as far as the time is concerned, if it does involve time. Also, if a question has multiple parts, make sure you're answering all parts of the question. And as usual, do not wait until the last minute to submit your work. Okay. Any questions about the homework? No? All right. I'm usually online via Slack after hours up to a certain point. So if you have a question, please pose your question to the Slack channel for the course. Because if you have a question, usually I find 9 times out of 10, a third to a half of your colleagues also have the same question. So it allows me to leverage my answer to you to everyone else in the class. All right. So where we left off, we talked about network applications. And if you think about what a network application is, it gives the illusion of some activity happening on, for example, your laptop. But in truth, what happens, there are parts of programs, there are processes rather, scattered around the network. Some of these parts are running on machine instances at a data center. Some of it is running on your machine. And they work together by exchanging messages to perform some function. If you think about things like Google Street View, right, you're going to go visit an area that you've never been to. So you look up the address and do a virtual drive-through, looking at all the landmarks, the streets, shops, and stuff like that to get a sense of what it's like to be there, so that when you do ultimately physically visit that city or town, you'll be a little bit more familiar with the surroundings. And so when you write programs, they will run on different end systems and they communicate together with one another over the network. For example, if you have a web server, right, and you connect to some website, maybe you're doing internet media streaming through Netflix or some such a type of internet property. You have your browser, which allows you to view that video, but then you also have the content itself that sits on the server somewhere in the data center. And so together, that allows you to watch a movie. Maybe you can rewind that movie. Maybe you can fast forward in that movie or click around asynchronously and look at various parts. And so a browser communicating with a web server is certainly an example, a very popular example, and very many applications piggyback or build upon web technology because it's there and it works. And so the nice part about this is that all the complexity is at the edge, right? And so if you consider our network diagram, at the edges or around the exterior of the network, you have the actual end systems or hosts, be they servers, be they laptops, mobile devices, and so forth. And so if you have a communication between, say, a server on one side of the internet and a client machine like a tablet on the other side, the software exists only at the end systems or hosts. It does not exist in the interior, namely among the packet switches. And that's really nice. If you keep the complexity at the edges, it means that you can make the interior, the packet switches, really, really fast, because the fewer moving parts something has, the simpler you can make it, and the simpler you can make it, you can make these simplifying assumptions and make it very, very fast and very, very efficient. In fact, on the high end, routers often implement that lookup against the forwarding table. That decision is often implemented in custom hardware, right? So you can get it to run really, really fast. But nonetheless, it's very easy to write a network application, and this allows you to very quickly stand up a new application. You just, look up some web programming interface standard. You look at some back-end technology. Many web servers support it. You just use it, and in the space of a week or two, you could put together a rudimentary web application. And so this makes it really, really easy to create an application, the fact that all the complexity is maintained at the edges. So if you think about it, you have your 5-layer internet stack at the edge systems or the hosts that the applications run on, and therefore all 5 layers, application down through physical layer, exist in our encapsulated layered approach for thinking about all the major components collectively that allow you to send and receive messages between your two endpoints. And so from the standpoint of the applications, each application layer believes, and I'll use that word specifically, believes that it's communicating directly with the application layer on the other side. So for example, one endpoint in your flow, in your network communication, would be your browser. That's an application. And then the web server, it is an application that's running as a process on some server machine somewhere in the data center, for example. And so when your browser sends your web request to the server, your browser thinks it's talking directly to the server. Now, in truth, we'll learn there's a lot of stuff happening underneath the covers as that message is passed from the application layer down into the transport, down to network, down to data link, and then encoded as signal energy on the physical layer, and then vice versa in the opposite direction on the receiver side. So yes, there's a lot of stuff happening, but from the standpoint of the viewpoint taken by the application, it has the illusion, if you will, that it is communicating directly with the other application layer instance on the other end system on the other side of the internet. Does that make sense? And so this also speaks to what we talked about last time as it pertains to layering, is that that special header and other information associated with each layer, it talks to or is meaningful to the similar layers that are in other parts of the internet architecture. Okay, does that make sense? Any questions? All right. So there are two different ways of organizing or structuring your network applications. As I said at the outset, that a network application consists of a bunch of processes that are effectively scattered about the internet running on these different end systems or hosts, and they communicate with one another. And so if you're going to arrange them, you need some general scheme or approach, if you will, of structuring all the components, all the processes that comprise your network application. And so one way of structuring your applications is so-called client-server architecture, and the other is so-called peer-to-peer architecture, which I'll define in the next slide. So client-server architecture consists of two processes, and these processes take on a certain role, right? And so one role is called the client role, and the other role is called the server role. Now, when I say role, I mean they serve some purpose, but they engage in certain types of behaviors. So let's begin with the server. The server is always on. It's always out there. And so, for example, Netflix's in their data center, or in Amazon's data center, or Disney's data center, those processes are running on some very powerful machines, and they're always running. They're always on. Moreover, these servers, they also are associated with machines that have so-called static internet addresses, internet protocol addresses, or static IP addresses. And the address is needed in order to identify that machine, because you can't push packets to a machine that you can't identify. And so a server is defined as being always on. It has a so-called permanent or static IP address. And oftentimes people aggregate these servers in high density and put them in one place, and that's called a data center, right? The whole purpose behind a data center is because you want to have a lot of computational power. So what you do is you have these units of computation, different machines, and you put a lot of them together in one place. And I'll explain in a few slides why you'd want to do that and the type of approach people take in doing that. The other role in the client-server architecture is called the client. And the client is the one that communicates with the server, and I'll be more specific about that than this slide and also that page in the book. The client is the role or that process that initiates the conversation, initiates the contact. The server just kind of sits there merrily running, waiting for someone to contact it, and the client starts that conversation, connecting with some request. And so in the case of internet, the web, your browser is the client. It contacts the server. The server's just waiting out there, just waiting, and all of a sudden it receives a message from your browser, right? So in the client-server architecture, the client is designated as that process that initiates the communication. Now, certainly the server, once it gets that communication, it responds to that request with some result of a computation, but it's the client that starts this whole interaction. The client, because it initiates the communication, the client also doesn't have to be connected all the time. It can be so-called occasionally connected or intermittently connected is the nomenclature or the verbiage they use in the book. So, when you use your web browser, you don't have your machine on all the time with the same IP address, right? When you're done using your laptop, maybe you close down your laptop. Your cell phone, a lot of these cell phones, because of the way mobile devices are, they'll go in idle mode. And one of the things they do when they're idle is they shut down communications. Because for mobile devices, one of the biggest users of your power budget on your mobile device is wireless communication, right? And so it's very typical for a machine to throttle back wireless bandwidth as a way to save power, right? So we have the client, it initiates the conversation or the communication with the server. It can be intermittently connected, and because it can be intermittently connected, there's no guarantee that you're going to have the same IP address or the same unique identifying address. And so you can also have a dynamic address. It can change. And it has to change, moreover, if you're connected to one network. So let's say you're here in the department or the division, and now it's called. And then let's say you close your laptop and you head to the airport. Well, the airport is going to have a different set of addresses, and when your machine is assigned an address, that's going to change. And so a client in this process, in this client-server architecture, can have a dynamically assigned or a dynamic IP address, and clients do not directly communicate with one another. When you are sending an instant messaging message or a text message to your friend, you're not sending it directly to him or her. You're sending it to a server, which is then sending it to that person, right? And so clients do not directly communicate with one another. Clients communicate with servers. Okay? Any questions about this? Does that make sense? Yeah. All right. So let's go further and take a look physically at what these servers are. So we're all familiar with clients because that's what we come in contact with throughout our typical usage of the internet. People have cell phones, maybe they have tablets, maybe they have watches, all sorts of devices, laptops, desktops, and so forth. But on the server side, modern servers are typically aggregated in high density in a data center. Now, this doesn't have to happen. Anyone can stand up or implement a server, right? As long as your machine, doesn't matter if it's a laptop, a watch, or what have you, but as long as your machine is always on, has a static or unchanging IP address, and just sits there, runs the software that waits your incoming requests, guess what? You're an honest to goodness server. Now, it might not be a particularly heavy duty or powerful or interesting server, right? That's debatable, but to be a server, all you need to do is just be continuously connected, have a static IP address, and you wait for incoming requests. Okay? All right. So this is what a typical server looks like, what you'd see in a data center. And it kind of looks on the left-hand side, it looks like a pizza box, right? And this pizza box, if you open it up, it has all the components you would see in a typical computer, but it's in a form factor specifically for this physical size. And this form factor, this pizza box, if you will, is usually accompanied by what looks like a cabinet, almost like a wardrobe, right? And these are typically made out of metal. I say medical, typically made out of metal. And these pizza box server instances, the server machine, will mount inside of this enclosure. And now this one has wheels on it, but some of them have wheels, some of them don't have wheels. And you can imagine you can have lots and lots of these screwed into this enclosure, kind of stacked up, and get a lot of computational horsepower in one small form factor. And so if we take these machines, these server machines are a standard height called 1U or 1 unit. And 1U is 1.75 inches tall, and there's a standard width and length for them. And they typically have these rails that are screwed onto the sides of them. And these rails have these wheels on them. And it's almost like a drawer, how you can pull out a drawer and push in a drawer, and it sits on wheels. Similar, these 1U server form factor units sit in rails, and they literally will slide using wheels once you put them in these tracks for the enclosure, and you can slide them in and slide them out. Now, the reason for that is because if you have a lot of these in a data center and you need to go maintain them and maybe change the hard drive or change a fan or add more RAM or something like that, you don't want to have to sit there and go through all sorts of contortions and stand on ladders and stuff like that in order to maintain these things. And so the design for a typical server enclosure, as it's called, rack-mounted server enclosure, is to have these things sit on rails, and you can literally pull these units out. You unscrew an anchor screw on the front, and then you just slide that thing out like you'd slide out a drawer. Okay. Now, a standard enclosure, this particular enclosure is a standard enclosure. It has enough of these 1U spaces, 1.75 inches, to fit 42 of these pizza box server enclosures. So oftentimes when you buy these things, one of the things they'll tell you is the height of this piece of equipment. Now, some servers will be a 1U server, right? And they'll tell you what the size is, and some will be 2U. You can get power supplies, and they'll tell you maybe it's a 2U or 3U power supply, meaning that it'll take up 3 of these 1 unit spaces in your enclosure. And so a 42U enclosure is what's called a full height enclosure, and that means you can fit 42 of these, or however many U's each one takes up, for all of your equipment that's mounted in one of these racks. Okay, and so you'll notice here on the side there are numbers in the middle of each of these sets of tick marks. Like here, this says 37, 38, 39, and it marks off each of the 42 U's for a full height 42U server rack or server enclosure. Any questions about this? Okay, so that's the mounting on rails that have wheels, just like drawers. You can pull them out and push them back in. So now you have the full populated 42U enclosure. You can put switches that are rack mount format. There are routers that are rack mount format. There are servers, there are power supplies. There are even monitors and keyboards that are mounted in configurations for server rack environments. And so you take each one of these full height 42U enclosures, and when they're fully populated, now certainly if you think about the wattage that a decent server in terms of power, decent server takes up, it's about anywhere from 700, 600 watts on the low end to it could be 2,000 watts on the high end. So you can imagine if you have 42 of these units, right? That's a lot of power these things are sinking. Right? And there's also a lot of heat these things are throwing off. You can imagine if you're doing a heavy computation on something as simple as your laptop and you're really driving your machine, you can hear the processor fan and all that stuff going. There's a lot of heat that this thing gives off. Even for something like sitting in the classroom, if you feel underneath your laptop, it's pretty warm on that table. Right? And so you can imagine if you have 42 of these units the size of a pizza box, each one is going full force running some computation. That's a tremendous amount of heat that each gives off, and it's a tremendous amount of electricity that each one takes up. So typically, these 1U or these multiple U units, the front of it would sit at the front of the rack, and as you push it in, the back of it, which is where you'd exhaust out all of that hot air as a byproduct of all of that wattage as it's churning through computations. And so you can take this enclosure, and it was a willful design where all of the heat generated is going to be wafted out the back of the enclosure. And these enclosures, the front and the back, are usually some sort of metal mesh, right? It's never glass. I mean, you might see some where the front is glass, but it's usually always mesh because you want to vent out all of that heat that's being consumed by your server rack mount units. And so if you take this 42U full height enclosure, you can actually design your data center, and data centers have a specific design. The whole building is intended specifically and purposed with housing lots and lots of these things. So you can imagine something that's like a warehouse size, like if you've ever been to a Costco or maybe I want to say I'll call it a super duper Walmart. It's a really large building. Maybe it's 200, 300, even more 1,000, 200,000 square feet, a big facility, but that building is designed specifically for hosting or holding a lot of these things. So typically what you'd have, you have a bunch of racks that are stood up next to one another, almost akin to the stacks of books in a library, but typically you'll have them in rows, in pairs, where in the back is where all of the hot air gets wafted out, and in the front, cold air is pulled in. And in some designs of data centers, you'll even pipe in cold air from the top through your HVAC system. And so you can imagine, if you suck up all the hot air from here and you push down cold air there, it just kind of circulates. The hot air goes out, gets cooled, and then cold air gets pulled in to keep this thing going. Because the better airflow you have for cool air on the inbound side, the harder you can drive all your server rack mounted server instances. Moreover, another thing they do, these facilities have so-called raised floors, right? And so you have the actual floor, which is typically the raw concrete slab for the data center, and then you have some metal framing, and then you have some support and some flooring above that. And so there's an air gap underneath the flooring that you would walk on, and cold air is usually pumped in that air gap, and you have some vents that come up in front of these rows of units, pushing air from here and then getting air in through the front. Okay? Any questions about this? Okay, so here is a depiction of one design for the airflow management, because when you design a data center, every last detail is engineered to the particulate, the dust content in the air, as well as the air channels and how air flows. And so in this particular example, you have hot air being sucked out the top of your units, cold air vented in through the raised floor grates here, but other designs do the opposite. They have the hot air wafted out there and the cold air wafted in there. And so, if you ever have opportunity to tour or visit a data center, you can ask them about their airflow management. And I'm sure the folks who do that will be more than happy to go on and on and on about their airflow management. So you can imagine this takes a lot of power, right? If you're cooling air, imagine just an air conditioner for a typical home, right? Central air. But could you imagine now the air conditioning for 200,000 square feet? That's a lot of air you have to push around. And so these data centers are very, very power hungry. And typically, when you locate a data center, you are always concerned not only just access to high-speed data pipes from your global service providers, you're also concerned about stable power. And so this is rendering, I think it's one of Facebook's data centers, and you'll see data centers next to things like hydroelectric dams, or not far from hydroelectric dams, near railroad tracks, because oftentimes people use railroad tracks nearby to run high voltage electrical wires, or you'll see them near power substations. So I know in Eastern Washington, in the potato fields of Eastern Washington, Washington State, you have a lot of data centers. In other parts of North Carolina. In Newark, Delaware, there's a data center in the area near the Amtrak rails. I forgot the name of the company. And there's a lot of data centers. There are a lot of them in the greater DC area. I just don't know specifically where they are. And so when you locate one of these buildings, right, it's designed specifically for data centers, and it is often located someplace where you have abundant and stable power sources, because these things are very power hungry, both for the cooling for the HVAC system and the chillers and the airflow and the blowers and the exchangers, but also the power that actually keeps the server instances running. Okay? All right. Any questions about that? Okay, so this is just a little bit of a view into data centers. And in fact, if you really are interested in the networking and system performance, there are a lot of opportunities in all sorts of companies to keep the data center operations going, as well as folks who design data flows for data centers. And if you think about something like Netflix, they're really, really concerned about having good performance, and they're also really concerned about continually monitoring and configuring and tuning all of the router infrastructure to make sure that all of the data flows into and out of their data center are relatively well balanced, so that you don't have a machine that's sitting idle. Okay? All right. Any questions about this? No? All right. So this is what a data center might look like, actual pictures. For example, you see your rows back to back, these machines. You have the front of the machines out here, and then you have here back to back, you have a little hallway here, and that's to help direct the airflow a little bit better. And of course, the floor, this is a raised floor, and this is what one might look like when you turn out the lights. You don't really need lighting in a data center unless you're going to actively maintain the components. And you might wonder, gosh, well, why do they have those colorful lights? Because oftentimes those lights will connote data access or hard drive status and so forth. And when you're walking the floor in this data center, a human maintenance person or a technician, you want visually some clue that there's something going awry with one of the server instances. Absolutely, they have what are called sensors, basically pieces of software that monitor all aspects or different aspects of the status of the server, but you also, it's nice to have visuals as to the status of the components in the data center. So that's why you see oftentimes these colorful lights associated with the various components in your rack-mounted enclosures. Okay. Any questions about this? No? All right. So what is peer-to-peer? We talked about client-server. Peer-to-peer is very related to client-server. And let me just take a segue to talk a little bit about what a peer is defined as. And this is slightly different from what the book says. This is just from my own experience working in the industry when I was in industry. And so let's say you have a process running, and let's call that process P1. And then you have another second process running, P2. And let's say process P1, it implements what I will call the client role, right? And process P2 implements what I will call the server role. And let's say P1 has some storage. I'll just kind of draw that as a drum, and that's your disk, right? And likewise, P2, process P2, has its storage, and I'll just draw that as a drum for your disk. Now, certainly, let's say P1, it initiates a request to P2. So P1 says, okay, here's a request, and I'll just call it rec, right? REQ. And that might be, for example, do you have this file, right? And that file could be like a music file, or it could be, some piece of software, maybe using something like BitTorrent or what have you, and you want to download a file quickly. And so you initiate a request, right? The client role initiates a request. So what does P2 server role do? Well, that server process looks in the disk and asks the question, okay, do I have that file? Let's assume that you have that file. So let me just say file here. I'll draw a box here. It does have the file. That request says, get this file. And so P2 gets that request. It makes sense of that request by chopping it up. What do you want me to do? And what do you want me to get, right? So it then does some work, right? That work is to now check its disk for the existence of that file. It finds the file, and it pulls the file into memory, and then pushes it back out as a response, RESP, response. Oops, let me do that more neatly, RESP, as a response back across the network to P1, right? So in effect, P2 has some resource that it provided or made available to the network, and P1 requested that resource. Okay, so that's a client and that's a server. Well, in a peer-to-peer network, the other view can also happen. You can have a server process running on P1, and then you can also have a client process running on P2. So what does that look like? Suppose you have a certain file. Maybe it's a music file or what have you. Suppose you have a different file. P1 has its disk, and it has that file. P2 can say, well, do you have this file? It initiates a request. Now, in that instance, because it's P2's client APIs or client processes or threads that are initiating a request, P2 in this interaction, it's acting like a client. So what does P1 do? It says, okay, let me check my disk to see if I have that file. If I do, it pulls it into memory and sends it back across the wire as a response back to P2. So in this case, P1 has a resource, and it's providing that resource and responding to a request initiated by P2. In the first instance, P1 was acting like the client. and P2 provided the resource. In the second instance, it was vice versa, right? And so any process that serves both the client and the server role, those are called peers, right? And so a peer is nothing more than a process that implements both the client and both the server role. Now, one of the things you'll notice here is if I have two peers, Peer 1 brings its resources, makes it available to the network. Peer 2 brings its resources, makes it available to the network. The more peers that I add that are reachable on the network that can communicate, the more resources I have available. Whenever you increase the number of participants in a network and those participants each bring their own resources, that's called self-scaling, right? That's why things like BitTorrent are really, really fast. Has anyone ever used BitTorrent? No? The uTorrent? Yes, it's a type of BitTorrent. And so what that means is if you have more peer instances running on the network, well, across all the peer instances, you can have more copies of different files. They might not all have the same files, but there'll be more files available, and therefore when you go to download, it's going to be much, much faster, right? This self-scalability is a really important benefit and a really important property associated with peer-to-peer architecture. So we have our peers, and with a peer-to-peer system, there's no server that's always on, right? Now, absolutely, there are processes that act like a server, but they don't have to be always on. Hence, in a peer-to-peer network, at any given moment, some peers might appear and some peers might go away, right? So they don't always have to be always on. And because of that, they don't always have a fixed IP address, but that can be taken care of with something that looks like an address book, an electronic address book. The moment a peer joins the network, they contact the address book, which is some server, and they register their address so that anyone who joins the network, they consult the address book and say, give me a list of 10 peers that are nearby, okay? So you don't have an always on server, and arbitrary end systems can communicate with one another. That means any two peers can engage in the client server type of relationship, that type of interaction, bless you. So any peer can contact any other peer in this setup. And so peers can request service from other peers, okay? They act like a client when they're requesting. Peers can also provide service in return to other peers. That's when you're acting like a server. And so when you have that, it's called self-scalability because each peer brings new service capacity. If you have 100 peers, you have 100 units of that service that is available for use. And so the reason why peer-to-peer systems are often more scalable is because with each one, yes, you have more demand, but you also have more services that are available. So there's something called peer-to-peer gaming, right? Peer-to-peer gaming networks are very scalable because of this self-scalability property. And so peers are intermittently or occasionally connected, and they can also change their IP address. And so the management of the availability is a little bit different from client-server architecture. Any questions about this? No? Make sense? Yeah. All right. So let's take a look at how these processes communicate. Now, if you took operating systems, I mean, many of you took operating systems with me, we talk about inter-process communication, the different means, whether it's shared memory or pipes. There's something called name pipes as well. They have multiple ways that processes on the same machine can communicate. Now, communication with whether it's client-server or peer-to-peer, these processes can be on different machines, right? So certainly the way you communicate is going to be different. And so these, how was it? Brain fart. Forgot what I was going to say. I said this already. I can't remember. Okay, yeah. So certainly, the role played by the 5-layer internet stack is purposed with implementing this ability to communicate between processes that aren't on the same machine. Okay, when you use internet communication between two processes on the same machine physically, it'll allow you to do that, and you use a special address called the loopback address. And underneath the covers, the loopback address just maps things to shared memory because it's a lot less expensive computationally to use shared memory if you're on the same machine than it is to use the network card. but it gives you the illusion that you're using the network. But underneath the covers, if you were to look at, say, a Linux source code, you'd see that loopback address maps to shared memory. Okay, so a socket is the name of the construct. It's a software API that allows you to communicate between two processes. You can use this socket to send and to receive messages between two processes on different machines. Now, it doesn't matter what language binding or language you're using or API on a different language. There are sockets in Python, there are sockets in Java, there are sockets in Swift, there's sockets in C, sockets in C++. Socket is just the name that's used for the construct that is the entry point at the application layer for sending information across the network. And so all processes, whether they're sending or receiving messages, they use a socket as the way to do that. And in the book, they draw the analogy between a socket and a doorway. So you can imagine if, all the classrooms along the hallway, you have doors on the classrooms, and imagine, in this weird version of the department, every time you opened a door and stepped into the hallway, this wind would gust and just blow you down the hallway into the next classroom through the doorway, if that doorway is open, right? You can think of a socket in similar fashion. And so the sending process, it shoves a message out the door, and the receiving process grabs that message from the hallway in through its doorway, right? And so the applications that are doing the sending and receiving on the socket, what they believe, or the perception or the appearance from the perspective of those applications, it appears that when I send something to this socket, put some information or some data into this socket, the other process gets it. When the other process writes something or puts information into the socket, I get it, right? The application is unaware of all this transport layer, network layer, link layer, and so forth, right? And so certainly in the implementation of the socket is going to take that information, that message from the application layer, and do something to it, the encapsulation, and send it down to the transport, down to the network, down to the link layer for physical encoding in the physical layer, right? So there's a lot of stuff happening, but from the perspective of the application, you just send something to the socket or read something from the socket, and you get that message or you send that message. Okay? All right, any questions about this? All right. And so even though the application doesn't know about the details in the layers below application layer, it just knows it sends and receives using a socket. As an application developer, if you want to write network applications, it's really important to understand the consequences of different alternatives that you can have for the underlying transport layer. Now remember, the transport layer, if you think about it, when you send something to a socket, you're actually getting data to go from the application layer, new information is added to it, and it goes down to the transport layer, right? And so that transport layer has certain services, not in the service client server definition of it, but that transport layer makes available certain features and functions that it can perform on behalf of the application layer. And so it's really important to know what sort of services is afforded to the application layer by the transport layer. Because if you choose wrongly in writing your application, you're going to have very, very poor results. If you choose well, then you're going to get the behavior you anticipated. Okay, so the first thing is about how you identify a machine, right? Because if you want to send a message to a host on the other side of the internet, you have to be able to identify it. And it's that identifier, in particular, a 32-bit identifier IP address. It has to be unique, which it is, and the router infrastructure understands that. And so ultimately, if you don't have a way of uniquely identifying the end system, the host, then that message that's sent by the application into the transport layer will never get there. So to receive messages, you have to have an identifier. And each host device, more correctly, each network interface card or network card, has a unique 32-bit number called the Internet Protocol or IP address. And that will guarantee that that packet or that unit of information will make it to the right machine. Now, of course, once you rank it to the right machine, you have to decide which application should I deliver this message to. Should I deliver it to the web server, or should I deliver it to the Dropbox storage server, or should I deliver it to the text messaging server, right? And so this IP address identifies the machine, but once you identify the machine, you now have to identify one of the many processes that are running on this machine, because the network card doesn't know who it should go to. It just knows I should get to the network card, to that network card, right? That's machine to machine delivery, which is facilitated by this IP address. So what your system uses, in particular the transport layer, is a so-called port number, right? And for certain standard, well-used applications, there are standard port numbers that are intended for specific types of usage. For the web, port number 80 is assumed to be the port number for the web, right? Now, of course, when you type www.somename.edu or what have you, you don't type a port number, but the browser is doing it for you as a convenience to make it easy. And so certain port numbers are intended for certain types of processes. There are processes involved in hypertext transfer, your web server and your web browser. So that uses the HTTP port, which is port 80. Then there's port 25, which is SMTP, Simple Mail Transfer Protocol. That's how email works, right? And so if you tried to send a web request to an email server, it would say, I have no idea what you're telling me, right? Because it's assuming your messages are going to be in a certain format and have certain values and have certain meaning. And so you have these things called port numbers, and these port numbers are pieces of information that are added by the transport layer to identify from which process a message came on the outbound side, and to which process a message should be delivered on the inbound side. So here, if you have your web browser running on your machine, you call send on a socket with the web request. It goes into the socket. Once it hits the transport layer, it says, that's your web browser. That's port 80. So it adds 80 to it, sends it across the internet. When it comes back out, transport layer says, who sent this? Port 80 did? Okay, that should be for the web server because 80 is for HTTP. So it sends that request to the correct application. Okay? All right. Any questions about this? So we have two pieces of information. One is the IP address, and that identifies the machine, or more correctly, the network card. And then the other is the port number. It identifies the application running on that machine, because you can have more than one process running on a single machine. Now, most laptops, and I see you all have laptops, most laptops have two different network cards, right? One is for wireless, and one is for wired. And for that reason, you will often have more than one IP address associated with it, right? You could conceivably attach to two different networks if you wanted to, and run your machine as a router. And we'll talk more about that. But you have different network cards, and if you were to all of a sudden plug your machine into the wired network, you'd have a different IP address versus now when you're connected to the wireless network. Okay. Any questions about this? Make sense? All right. So we have port numbers to distinguish or to identify the process that is the source or the destination for that particular packet. All right. So when we talk about protocol, I alluded to this idea of what would happen if you sent a web request to your email server. You could absolutely do that, and it wouldn't understand what you're talking about. It's just like if you learned the rules of German and I learned the rules of French, and I started talking French to you, you would not know what I'm talking about because there's no meaning to that information that's going across. And so enter the application layer protocol. The protocol defines the type of messages that you exchange. So what is the format of the request? What is the format of the response? It describes the message syntax. What are the different fields that describe this message? And what values can these different fields take on? It also describes what's called the message semantics. When you see certain values in certain fields, what do you do as a server? When you have certain values in certain fields, what do you do as a client? So there is the structure, there is the values that are in there, and then the behaviors or semantics that you engage in, both the client and the server, when you get a particular type of message. All of that together defines a set of rules about how to respond both on the client side and their server side. And this is called your protocol. Now, there are all sorts of protocols that you know about. SMTP is Simple Mail Transfer Protocol that defines all of these things as it pertains to email. HTTP, Hypertext Transfer Protocol, which is what the web is based on, that describes all of these things, the structure, the semantics, and so forth, for the roles for the client, i.e. the web browser, and the server, i.e. the web server, right? And so all of these protocols are well known, these public protocols, HTTP, SMTP, there's DNS, there's all sorts of stuff. Then there are proprietary protocols, they're corporate secrets, things like Skype, right? You can try to reverse engineer any protocol using Wireshark, but for the most part, you're never going to get protocol documents telling you what these protocols are because they're considered to be competitive advantage. So for example, if you have an Xbox or video game console, you're playing a game, you could absolutely run Wireshark and intercept the packets and try to figure out what's going on. But if you were to call up Microsoft and say, can I have the protocol for the communication between peers in a particular game, they'll say no, absolutely not, because that's their proprietary secret. And so there are public or open protocols, and these open protocols are the basis of a lot of these standards that define internet communication. And these things are not secret because they're published in something called requests for comment, RFC, right? And so you can look up the RFC for HTTP, version 1.1, and it'll be there in all its splendor and glory. So if you had an idea for a specialized web server, you just look up the RFC for the particular version of HTTP, implement your web server to that standard, and then you're guaranteed that your web server will interoperate with every web browser. Okay, that's why open standards are very, very important. Proprietary companies can do that because they make the client and the server, but for the open standards, what it means is that your browser by Google Chrome, running on Ubuntu Linux will always work with a web server running on Microsoft Windows, and you can choose any client, any server implementation, any operating system, and it'll all work, right? And that's because of these open standards, these open protocol definitions. Okay. Any questions about this? Does that make sense? Okay. So what does an application need from the transport layer? Well, it depends on your application, right? Some might need so-called data integrity. What does data integrity mean? It means that what you send is what the other endpoint receives. That's really, really important. If you send 0111, deposit $7, you don't want it to arrive and be 1111, deposit $15, right? So this data integrity says that you have 100% reliable data transfer. Now, reliable means not only are the bits that you originally send not corrupted, but it also means that they're sent they arrive or they are delivered to the receiver in the same order in which you send them, right? So if you said, here's a bank balance, deposit $100, and then withdraw 75, right? If your starting balance is say 25 and they come out of order, well, that withdrawal is going to get rejected, right? And so this idea of data integrity not only refers to the integrity of the data, meaning the data is not corrupted, but it also refers to the order of delivery. The order in which you send them is the order in which they are delivered to the other endpoint. And we'll describe ad nauseum in great detail about how that's implemented when we get to the chapter on transport layer. There are applications like file transfer and transactions. File transfer, if you're transferring an executable file, maybe you're downloading a JDK, you're installing NetBeans or what have you, you want those bits that are received in the same order that they're sent, or else that executable is not going to run. It's going to get garbled. Likewise, you don't want those bits to get corrupted when they're delivered. You want them to be the same bits that were sent because it's not going to run if it gets corrupted. There are other applications, such as audio, where you can tolerate some loss of data and some corruption of data. Right? Sometimes you listen to audio streams, something kind of skips, you just rewind and say replay it, or you just say, no big deal, right? So some applications can tolerate losses, but other applications, data integrity is very, very important. Okay. Timing. So there are some applications for which timing is really important, that you have a very low delay and you have guarantees on this low delay. And so some applications like internet telephones, IP phones, right? When you are talking on a phone, you don't want to say hello and then maybe 5 minutes later they hear the hello, right? You want to guarantee it works. You can tolerate some loss. You're like, come again? I can't hear you, right? And they say what they're saying again. But the delay, the timing here is really, really important for internet telephone apps. Now, I remember back during more early days in the dot-com boom when IP phones were just kind of really getting started. Um, a good friend of mine was stationed overseas, and we were trying to do IP phone. It wasn't really IP phone; it was just a microphone attached to a computer. Um, and it was just horrible. It worked, but it was like talking on a scratchy CD, right? Because stuff was getting corrupted, stuff would take too long. You hear an echo, there's all sorts of weird stuff going on. But it's pretty darn good today. You don't even have to really rig something custom with a microphone and computer. You just subscribe to Vonage or Magic Jack and you just have your phone. And the beauty of IP phones is that you have the same phone number, and anywhere you go, as long as you can get an internet connection, you're connected and someone can call you. So how awesome is that? You know, you travel to a conference somewhere, you're anywhere in the world, you just plug in and people can call you and talk to you as if you were just at home on your regular phone. I'm not advocating for a particular product. If Magic Jack wants to sponsor me, then sponsor the class, then they're happy if you're listening. But anyways, so we have internet telephone or IP phone applications. Okay, throughput. So some applications need a guarantee on throughput. That's about the bandwidth, the rate at which bits per second are pushed through that connection, your end-to-end flow. Things like video conferencing, things like multimedia, you want good throughput because if it's really, really, really doggedly slow, it's not going to be an enjoyable experience, right? And so throughput, other apps are called elastic apps, and these elastic apps um, they want as much bandwidth as they can get, right? And so these apps are things that if you have a megabit per second, it'll use up a megabit per second. If all of a sudden it increases to 100 megabit per second, it'll use up 100 megabit per second. So there are some types of apps where it wants to use up as much bandwidth as possible, right? And so when you think about how you write your applications, you have to first think about the needs of the application. Do you need data integrity? Do you need some timing guarantee? Do you need a certain type of throughput? Or do you want all the bandwidth you can get if you can get it? Okay? All right, any questions about this? All right, so, and then of course, security. That's obvious, right? There's a lot of sensitive information, and you don't want people to have access to that sensitive information. Now, certainly, I cannot do justice to the security part in a course like this because the focus of this course is networking, not network security, which is its own field. I'm not sure if we still have it, but there are some security courses, I think, they've sort of been reduced since our security person left, but nonetheless, security is very important. So I'm not going to go through this whole table. This is in the book, and it talks about certain types of applications and the needs they have or require from the underlying transport layer. So if you're dealing with file transfer, you cannot afford data loss. So whatever transport mechanism you use, if you're going to implement the file transfer program, and that could be file transfer like secure copy, or it could be something like Dropbox. Dropbox is in effect a file transfer program. It's just synchronizing and doing stuff for you. And so you can't afford data loss. You have to have data integrity for file transfer because that file will not be the file that runs or that you can see. Throughput is elastic, right, for file transfer. The more bandwidth you have, the faster the file transfer. So if you all of a sudden, for a moment, had a gigabit per second of bandwidth, the file transfer is going to want to use that because it wants to get the file there really, really fast as possible. And then time sensitive. No, it's not time sensitive. If you get the file in 10 minutes versus 5 minutes, well, your impatience doesn't really matter. But as far as the integrity of the interaction for file transfer, it doesn't matter if it takes 5 minutes or 20 minutes, right? So that's not an important concern, key to the functioning of the application. But if we take, for example, something like stored audio and video, right? You're doing video streaming or audio streaming. You can afford to relax data integrity, right? You can afford to lose a little bit of data as you're pushing this audio or video data across the wire. Throughput, yeah, you want to have good throughput. In fact, audio and video up to the maximum bandwidth needs, you want to have as much bandwidth as possible for audio. In fact, one of the things we'll talk about this semester is Dash. And Dash is a streaming protocol that says, based on the performance of the bandwidth of the pipe, I can send different resolutions for the video. So maybe you have something that's high def, maybe something that's a little bit lower definition, a little bit lower, and then based on the performance of that flow across the end-to-end flow, it'll reduce the resolution because a reduced resolution requires less bandwidth. So it'll adjust the resolution in response to the performance that's perceived for the end-to-end flow, right? And there's something that like folks like YouTube, Netflix, if not Dash in its plain vanilla form, they use some sort of variant. And if you're ever watching YouTube or some streaming video, you notice sometimes if your network is slow, the resolution will start to get a little blurry, or maybe the pixels will look a lot thicker and not as fine grained. And that's because it's adjusting resolution to try to keep your video going in the face of reduced bandwidth. Okay, so what are the two services or the major services? These aren't the only two, but 99% of the time people are using one of these for the transport layer when you create a socket in an application. One is called TCP, Transmission Control Service, and TCP has the following attributes. It offers reliable service, reliable transport. So between the sending and receiving endpoint, it always guarantees that your bits are received or delivered to the endpoint in the same order in which you sent them. It also checks to see if your packets are corrupted and will recover from that. Or if a packet is lost, it'll recover from that as well. So it's a reliable transport, and it does what's called flow control. Now, certainly, if you're going to deliver packets in the same order in which they were sent, if something arrives out of order, you have to store it someplace until you get the in-order things and then deliver it to the application. And so what happens is you have one of the resources you need in order to engage in this end-to-end communication is you need some buffer storage space because you need to assemble that data because some of it could come out of order, right? And so what flow control does, it communicates between the sender and receiver endpoint, and it can adjust the rate of sending if the receiver is running out of storage space, right? Then there's another thing that TCP offers, something called congestion control. If the routers along the path between the sender and receiver are experiencing congestion, what happens? Well, you have congestion delay, you have the nodal delay. Now, certainly if you're congested, it means that the router buffers or the router queues are relatively full, and that means that your packets are going to wait longer, which means your end-to-end flow is going to be slower. And so TCP has a mechanism that we'll learn about for doing congestion control. And what it does is it reduces the send rate between the sender and receiver if it detects that routers along the pathway are experiencing congestion, because you don't want to get to a point where you're going to have data loss a whole packet. And as you're going from one hop to the next, to the next, to the next, if you drop a packet closer to the destination, it's more quote unquote expensive. And I'll draw a diagram to explain what I mean by that. So suppose you have a host here. Let's call that, let's see, let me get my other marker. Let's see if this one works. Okay. Suppose you have a host, this host on the left on the board, and call that host 1. And let's say you have another host here. Let's call that host 2. And so host 1 goes to some router. Let's call that router 1, R1. And then there's router R2. And let's just say there are 10 routers, R10, between the source and destination. So you have 1, 2, 3, 4, 5, 10. You have 11 hops to get between the source and the destination. Now, if you pass a packet from host 1, okay, it's stored and forwarded on router 1, stored and forwarded by router 2, and so forth. Now, certainly host 1 and host 2 aren't the only hosts using those routers. You have other connections coming in along the way, pushing traffic onto each one of these routers. So let's say this packet, let's call that packet P1. It gets transmitted in router 1, transmitted to router 2, and so forth. And now it gets to router 10, and let's say the buffers in router 10 are completely full. Well, when a packet arrives at a router, if the buffers are completely full, it has to drop that packet. Now, if you drop this packet here, now what ends up happening, TCP will learn, ends up resending it, right? And so if you drop the packet right at router 10, you've already, you being the network or the flow, gone through all that work of looking in the lookup table, transmitting it, looking at the lookup table, transmitting it. You've done all that work, only right at the last step, you drop it and you throw it all away. And so you don't store packets at previous routers to check if it got there. That doesn't happen. It's only at the endpoints, because to do that at the routers, you would add too much complexity to the network infrastructure. And so, in essence, it gets more and more expensive. If you were to drop it here at R1, okay, well, you just send it along one hop. If you were to drop it here, it's twice as much. Now, if you get all the way to R10 and that packet gets dropped there, it's the most expensive. And so the closer to the destination that a packet is dropped, the more expensive that flow is, because the time that it took for it to get there, you have to repeat that, and it's a large amount of time. And so how might you see that in something like your Netflix application? Well, if that packet got all the way there, maybe that's a frame or some segment or part of your video, and all of a sudden it gets dropped here. Now the previous video displayed, or the previous, maybe second or two of video displayed, and all of a sudden you don't get the next delta T of video until a really long time from that, right? And so you really want to minimize this idea of dropping packets at the router, because it gets more and more and more expensive computationally as well as time-wise the closer you get to the destination, right? And so what TCP does, it uses this congestion control to slow down the rate at which the sender is sending packets into the wire if it detects that routers are getting congested, right? And there are mechanisms for inferring that. Okay. TCP does not provide any timing guarantee or security. And the reason for no timing guarantee is that when you're doing statistical sharing and not reserving bandwidth, like circuit switching, you can't have timing guarantees if you're doing statistical sharing. 101. And it's also connection oriented. And what this connection oriented means is that you have to establish the resources before you can communicate. And what that means is host 1, before it can communicate with host 2, it has to ask host 2, do you have the resources needed in order to engage in all of those aspects of the protocol that give you this reliable transport, right? And that includes buffers, that includes timers, and a bunch of other stuff that we'll talk about. And so that's called connection setup. You have to first exchange a message between the sender and receiver, host 1 or host 2. Do you have these resources? If it has them, it says, yes, I do, I'm ready, and it returns back a message to say, yes, I have these resources. Now, all of that comes at a cost. All of this reliability, it takes computation to do all this checking and this resending and this constructing of out-of-order packets for delivery in order and stuff like that. And what the cost of that is that when you have a reliable channel of communication, you're going to have slower bandwidth, because some of that bandwidth is used in maintenance of the pathway between the sender-receiver endpoints, as well as for the error checking and the resending and the buffering and delivery. Okay? All right, any questions about this? Yes. Mm-hmm. Yes. Mm-hmm. Yes. So that is an implementation in the application layer to try to get past that loss, and I'll explain that in a second. Let me just do the unreliable, because that's exactly what they do. So with the unreliable data transfer, you don't have any of these guarantees, and because you don't have any of these guarantees, that means you can have communication much, much faster, but you're more susceptible to have a packet that's lost or something that's dropped. And so it doesn't provide UDP, unreliable datagram service. It doesn't provide any of these guarantees. Now, to answer your question, at the application layer, what some application implementers say, they say, okay, well, I know that I could get some congestion, and I want my communication, my streaming of this video to be very, very fast, right? Because the faster I can send data between the communicating endpoints, the more video I can get, especially if I'm doing high def. So they look at their setup and they say, gosh, well, I think that I will never lose so much data that I will have a gap of longer than 5 seconds of video or longer than 10 seconds of video. So what I'm going to do before I start up this application, I'm going to fill 5 seconds worth of video into a buffer. And then every subsequent packet containing video information, I'm going to use that to populate my buffer. And then when I display the video at the client side, I'm just going to display that video out of my buffer, right? So you notice if you have a lot of loss, sometimes your video will pause and it'll say buffering, and you see that buffer, that depiction of the buffer fill. And so what they do is they put an upper bound on if the network goes completely to hell, maybe I'll lose 10 seconds of video. So I'm going to have a buffer that can hold 10 seconds of video, for example, or it could be 5 seconds of video, which is why you'll also notice if you ever you have a network cable, you can do it with your network card too for wireless. You watch something like YouTube, right? And then you disconnect your network connection. You'll still be able to play a little bit of video even though your network is disconnected. The moment you disconnect your network card, whether it's turn off your network antenna or unplug your cable, you're not getting any more packets, right? But it can still display video because it's reading it out of the buffer instead of directly from the network card. Okay? So to answer your question, it's application level buffering. And they use that as a trade-off to say, I can use the unreliable service underneath the covers. And as long as I buffer, and it's an uneducated guess, as long as I buffer a certain amount worth of data, then maybe that buffer will be drained down halfway. And then once the network recovers, it fills back up again. And maybe it'll be drained down like almost all the way to the end, and then the network recovers and it'll start filling it back again. Okay? All right. And you see this with set-top boxes these streaming like Roku and Hulu boxes and stuff like that. You see that all the time. Okay. Any questions about this? Other questions? Make sense? Okay. So let's see, the time is 1:06. So this is a listing of different popular applications as well as the RFC, request for comments number, and this is something you can Google search and just see the document. They're not the most interesting things to read. How interesting is 2 bytes has this value, do this behavior, but nonetheless they're there if you want to implement something that uses these protocols. And so SMTP is RFC 2821, and SMTP uses transmission control protocol, the reliable service, as the underlying transport. If you think about what happens in email, email has text in it, it has other rich media. You can't afford that text or rich media, the bits for them to be corrupted and out of order because the order means something, right? Or else you don't get text, you don't get proper video. If we look at something like streaming multimedia, like YouTube, some will use TCP, because they made the trade-off that they want reliability, albeit it's at a slower rate because of all this error checking. Some of them will use UDP, but they supplement that with application layer buffering. Okay, and that trade-off is that they would rather have the raw speed afforded by not doing any error checking, which is what UDP is. Okay, any questions about this? So this is also in the book. I'm not going to go through all of them. Leave it up to you to do that. And so TCP originally was not intended to be secure, right? People added security mechanisms on top of that. And so in the early days of email, and I remember this, it wasn't that long ago, you would type in your username and password, and your username and your password just go across the wire. So of course, somebody with Wireshark could just, get that, intercept it, and just have your password and go to town. So as more aspects of society made their way onto the internet, so too did crime related to information stealing and stuff like that. And so TCP does not have encryption and a technology called SSL, Secure Sockets Layer. So we just said a socket is that API that sends data to the network or receives data from the network. Well, what SSL does, it encrypts that data, so it's a user level, it's an application level API library, and there are various libraries that people have written. And so it accepts your message from your application, it performs encryption, and then sends it into the transport layer. So you can think of it as an encrypting version of a socket, and it's called SSL or Secure Sockets Layer. And so this provides you an encrypted TCP connection, and sometimes when you go to a website, you'll see your URL change to HTTPS. That S stands for Secure Sockets Layer, right? And that little lock symbol, if you click on that, that'll show you the certificate associated with this encrypted connection. Now, there's something else called endpoint authentication. Maybe if time permits, I will talk about that. Endpoint authentication is a way of identifying, is this server I'm connected to really the server I think it is, right? And that's to help protect against spoofing, right? Just because you go to WSFSbank.com, it doesn't mean it's WSFSbank.com. It could be someone else that is taking your request and forwarding it to the real website. And so when you click that certificate has been validated, I'll say it that way at this juncture, validated by a third party to say, yep, this really is WSFS Bank that you're talking to, the server. So SSL sits at the application layer, right? And so you can imagine, now you don't have to use SSL, but it's a good idea to use it because it's very well done and been around for a while and debugged and stuff like that. But there's nothing precluding you from encrypting your data yourself and then sending it out a regular socket. There's absolutely nothing stopping you from doing that. But since SSL has kind of stood the test of time for a while and people are constantly improving it, you might as well use what's out there, right? Okay, so it sits at the application layer, and these applications use SSL libraries, and these SSL libraries interface with TCP. TCP doesn't do encryption, but this SSL does the encryption and the decryption on the inbound side. Okay? Any questions about this? All right. So let's start. It's 1:11, so I don't have much time. So I'll just introduce this idea about the web and HTTP. Now, when you look at a web page is what's called a semi-structured document. It's a document, and it has all sorts of attributes. Like it has a color, it has different sections and fields, and these fields can have text in them. They can be different types of widgets like buttons and drop-down lists. You can also have images. You can have animated images. You can have videos. You can have executable content like a Java applet. So the web is this web page. And it can also have links. I forgot about links. A web page is a document, and you can think of this document as consisting as a collection of objects, right? These objects all come from somewhere. The web document itself also comes from somewhere. And so what this hypertext transfer protocol is, it's a scheme, a protocol, so it's a format of messages and values in those fields, and certain behaviors happen both at the client side and the server side when you have certain values in certain fields. And so what this HTTP does, you have a description called a URL, a Uniform Resource Locator, and it's essentially, you can think of it as a distributed file system, right? Not a proper distributed file system, but nonetheless, you have a collection of objects that are located on different machines, and you can identify these machines by some address, right? And so the structure of a URL, you have a host name, and we'll talk about DNS in terms of how you map this host name to an IP address, but this is the identifier for a particular machine. So you have the host name part of your identification. You also have a path, so it's a directory, right? If you don't have a path name, believe me, your website, your web server has what's called a root file system. It has the beginning part of its file system that it manages. And then you have some paths, it could be directories, and then ultimately you have the name of the resource, right? If this is a GIF file, picture.gif, or it could be an HTML file, hypertext markup language file, index.html, or some other HTML file. So all of this together identifies this GIF in this directory on this machine's hard drive, right? And so when you have a link, that link is just one of these type of web addresses, the URL. And so what HTTP is, it's a mechanism, a protocol that allows clients to request web objects from machines scattered around the internet. Okay? All right. Any questions about this? So it's now 11:14. We will end there, and we'll pick back up with this on Tuesday. I look forward to your submissions this evening. Okay, we'll end there. I'll see you Tuesday.